Hi everyone, happy Wednesday. As you know, it's time for the Chem Help ASAP live stream. As you can tell from the title and my moderator, we are going to be working on different aspects of solubilities. So we'll start with solubility rules and we'll do some molecular, complete ionic, and net ionic equations. And then we'll add in a little bit of solution stoichiometry kind of at the end. So anyway, I hope you find this live stream helpful. Let me know any questions you have in the comment section, and let's go ahead and get started. Okay, so here is where we're just really going to use our solubility rules and just write some reactions and not mess with too much math here. So what I've done is I have put in the solubility rules here. Now these are just very, very general solubility rules. And depending on the class you're taking, your solubility rules might be a little bit different. They might have more ions in here. They do vary just a little bit depending on what textbook you're using or what class you're taking. But these are the ones that we will use today for this live stream. But don't panic if you're using a set that's just a little bit different. Okay, so for this first multi-part problem, all we're going to do is we're going to react two compounds, and we want to write the molecular, the complete ionic, and the net ionic equation for each of these. So we'll just work our way through, and I'm hoping that I've got enough space on this page, but now I'm wondering if I do. Anyway, we'll just start and we'll see what we've got. Okay, so we'll start with problem A, which is ammonium sulfate and barium nitrate. So we'll start with the molecular equation because that is going to be our easiest, and we will move from there. Okay, so this is part A. So we have ammonium. Let's see, we're going to need two of these for sulfate, and we're reacting it with barium. We're going to need two nitrates. And look, I'm not even going to have enough space to write this reaction. Okay, so what I'm going to do first is I'm just going to predict products. Now, this reaction is a double replacement reaction, and I'll explain how I know that first because, how do you know that? So what we've got is we've got two ionic compounds, and you can think of this even, maybe I'll do this, as AB plus CD. So we've got a cation and an anion in both of these compounds. And what's going to happen is they're going to swap. So you can either swap cations or you can swap anions. It really doesn't make a difference. But we're just going to flip either the A and C or the B and D. So what I am going to do is I think I'll flip-flop anions. I mean, why not? So we'll make this, actually I'm going to come down underneath because I don't have a lot of space here. So you can see I'm taking my cation, my A from my first compound, and I'm going to use the anion from the second compound, or my D. So that is going to be ammonium nitrate plus, and again, I'm going to go barium. This is my cation from my second compound, and sulfate. Now, what I am also doing that I guess I'm not really specifying here is I am making neutral compounds. I'm just going ahead and doing this. So ammonium I know has a +1 charge. Sulfate has a -2, which is why I have two ammonium cations in my reactants and only one in my product because now I've got a +1 and a -1. So when you're writing these reactions, and usually by the time you get to solubility rules, hopefully like your polyatomic ions are memorized, or at least very close to memorized. And also your monoatomic ions, either they're memorized or you can just look at the periodic table and know what they are. But I am not going through all the calculations on how I'm making neutral compounds, but I am making neutral compounds. Otherwise, you won't get these things to balance at all. Okay, so back to my reaction. So hopefully you can see in my products what I've got is I have, again, cation A, anion D, plus cation C and anion B. Now remember, when you're writing these, you always write the cation first and the anion second. So A and D and C and B, not B and C. Just always write that cation first. But we need to balance, and then we need to determine states. I'm not going to have enough space. There's no way. All right, so let's balance first. I have 2 ammonia. That gives me 2 nitrate, which I already have. Okay, so that one was super easy to balance. Now let's put in states. So what I'm really looking for is if something is soluble, I'm going to call it aqueous or AQ. And if something is insoluble, if it's going to precipitate out, then it's going to precipitate out as a solid. So it will have an S after it. So if I am looking at my ammonium sulfate, and I go back to my rules here. So let's go to the rules and let's determine these. Ammonium sulfate. So I do have a rule for ammonium up here. You can see it's under mostly soluble ions, and there are no exceptions, meaning any ionic compound that has ammonium as the cation is going to be soluble. I can also check this with my rules for sulfates, which I have right here. Again, sulfates are mostly soluble. These exceptions are ones that are insoluble. So using either rule, ammonium sulfate is going to be soluble. So I am going to put, maybe I'll do it in green, I'm going to have to move this plus. I'm going to put an AQ in parentheses afterwards. And let me put that plus back in. Okay, so I'm going to do the same thing with my barium nitrate. So usually these are done by anions, but you can look at cations as well. So I'm not seeing like any rules for barium that really pop out, but nitrate definitely has a rule. It is mostly soluble. There are no exceptions, meaning anything that is an ionic compound with nitrate is going to be soluble. Hence, barium nitrate is going to be soluble, and I am going to put an AQ there. Okay, on to products. I have ammonium nitrate. Again, ammonium is soluble and nitrate soluble. So this is like double whammy soluble. And now barium sulfate. I'm going to go look at my sulfate rules. So here are my sulfate rules. It's mostly soluble, but you can see barium here is one of my exceptions, meaning that most sulfate salts are soluble, but barium happens to be one of the insoluble salts. So barium sulfate is going to precipitate out of this reaction, meaning it is not aqueous. It is going to form a solid. Okay, so here is my molecular equation. Now what I want to do next is I want to write my complete ionic equation. And what this does is this is going to take all of my soluble salts and it's going to break it up into cation and anion. So taking my first salt, my ammonium sulfate, instead of writing it as ammonium sulfate as a bonded molecule, I'm going to write it as a cation and an anion. So I'm going to have ammonium and I'm going to have sulfate. This is not yet complete because if you look at ammonium sulfate, of course, I have 2 ammonium cations, not just one. So I'm going to put a 2 in front of my ammonium. And these are obviously soluble. So I'm also going to write AQ after each ion. So this is soluble and this is soluble. And obviously, if you are taking an ionic compound and you are breaking it into cation and anion, I'm trying to think if there's any time where you would not write aqueous, because if they do not, if it's not soluble and you don't get a cation and anion, then it would be a solid. So anytime you see a cation or an anion written alone in a reaction, it should have AQ afterwards because it's aqueous, it's soluble. Okay, so that's ammonium sulfate. We're just going to continue on. I'm going to do the same thing with barium nitrate. So we have my barium cation. It has a charge of +2. Yes, it is soluble. And nitrate, I've got 2 of them. And that is also aqueous. And I am just going to go down to my second line here. And I'm going to do the same thing, again, continuing with all my soluble salts, which means ammonium nitrate soluble, so it is going to break apart into my cations and anions. Notice I am using a 2 in front of my ammonium. That's the stoichiometric coefficient because I have a 2 right there from my balanced chemical equation. Yes, ammonium is aqueous, and now I still have 2 nitrates. They are aqueous. And finally, my barium sulfate is not aqueous. It is a solid, so it remains like this. So here is my complete ionic equation. What you want to do is you want to make sure that you still have a balanced equation so that you haven't missed, say, a subscript or a stoichiometric coefficient. If your molecular equation is balanced, then your complete ionic equation should hopefully also come out balanced, but it's easy to forget something. So in this particular example, I would say students who do this problem are probably going to forget this 2 right here on the nitrate because they forget that this stoichiometric coefficient applies not just to the ammonium but also to the nitrate. But you can see we've got 2 ammoniums, 1 sulfate, 1 barium, and 2 nitrates. So we have a balanced, complete ionic equation. Okay, I just want to make sure. Oh, hello, Mr. White. Hello from Belgium. Oh, yes, you've got a question. Good books to learn chemistry by. If you want to start at the beginning of chemistry and just learn it like a class, I highly recommend Khan Academy and just starting with their chemistry course, because not only are they going to start you at the beginning and provide really nice content, but then they also give you assessments so you can practice doing problems and you can see how you're doing. So I'm really a huge fan of Khan Academy, especially if you want a complete course in chemistry as well. And of course, you can always join us for live streams if you've got any questions. Okay, so back to our complete ionic equation. So to go from complete ionic to net ionic equation, what we want to do is we want to get rid of what are called spectator ions. And spectator ions are just ions that you find on the reactant side and the product side. They haven't done anything. They've remained exactly the same. So we have several spectator ions, and I'm actually going to cross these out in red. So I'm going to take my complete ionic equation, and I am going to literally cross out anything that is same on the reactant side and the product side. Now it has to be exactly the same. So if you look, you can see my ammonias. Not only is it both ammonia and it's soluble, but I have 2 of them, so I can get rid of these. Those are spectator ions. So I'm looking for the same thing. I cannot cross out anything with sulfate because on the reactant side it is aqueous and on the product side it is now a solid. So those are not the same thing. The same is true for barium, but you can see my nitrates. Again, I have 2 on the reactant side, 2 on the product side. They're both aqueous, so those can go as well. And now what I'm going to do is I'm going to rewrite my crossed out complete ionic equation, and that will give me my net ionic equation. Okay, so net ionic equation for this is going to be my sulfate plus my barium, and that is going to give me barium sulfate solid. Oops, I forgot my aqueous on my barium ion. Double check, make sure it's balanced. Yes, it is balanced. So that is our net ionic equation. And this is very typical that you'll start with, especially your complete ionic equation is going to be very long and involved, and then it'll simplify down to something very short and very easy. And again, if you've pulled kind of everything down correctly, then when you write your net ionic equation, it should already be balanced, but it's of course always nice to double check. Okay, that was only A. There's no way I am fitting this in to everything. Okay, maybe I can fit in part B down here if I'm careful and I write small. So what we've got for B is lead 2 nitrate and sodium chloride. So this, again, I'm not necessarily going through naming rules here, but this is a transition metal. They have given you the oxidation state of the lead. All right, so lead 2 nitrate is going to look like this. Again, I'm going to make neutral compounds here, plus sodium chloride. And now I'm going to predict products. It's going to be the same thing. This is a double replacement reaction. So again, either flip-flop cations or anions, however you want to do it. So I am going to go with sodium nitrate. And this is still lead 2. It has not changed oxidation states. So now this is lead 2 chloride. If you change oxidation states, that is a redox equation, and we are not going to deal with redox today. Okay, so here is my chemical equation. Let's balance it. I'm going to need a 2 here and a 2 there. That gives me 2 nitrates. And so that is a balanced equation. Now to check my solubility rules and decide what is going to be aqueous and what is going to be solid, if anything. Okay, so looking at lead nitrate first. There's not really going to be a rule for lead, although you'll see there are exceptions for lead. So let's go for nitrates. So nitrates, again, there are no exceptions. They are soluble. So lead nitrate is soluble. That's aqueous. Sodium chloride, hopefully you already know this off the top of your head. This is table salt. Yes, it is soluble. You probably know that just from experience. But you can see we've got the alkali metals, including sodium, are all soluble. And here you can see your chloride anion is also soluble, and these are the exceptions, but obviously sodium is not part of that exception, so sodium chloride is soluble. Now we go to sodium nitrate. Again, nitrates are soluble, your sodiums are also going to be soluble. And so now we've got lead chloride. So again, if I go to chlorides, I can see chlorides are mostly soluble, but a lead 2 is an exception, meaning that lead 2 chloride is insoluble. So I'm going to put an S there. So that is my molecular equation. It's balanced, and I have put in all of my states. Okay, now we need to go on to my complete ionic equation. And just to separate these two problems a little bit, there we go. Because my complete ionic equation, again, is going to be very, very long. So I think I'm going to start at the far left here. Okay, so lead nitrate is soluble. So I'm going to split it up into cation and anion. So we have lead 2. And we have nitrate. Remember, there are, oh, sorry, I wrote that as a 3. That should be a 2. That is my mistake. Apparently, I got very happy with the 3. I did it again. Apparently, it's just too late in the evening for me to think that is lead 2 nitrate, not lead 3. Okay, so I have 2 nitrates. This is why you always check your work. Because even when you've done it many times, it's easy to make a mistake. Okay, so that is lead 2 nitrate. Let's go on to our sodium chloride. Again, it's aqueous. Don't forget you've got a stoichiometric coefficient. That is a 2. So you're going to have 2 sodium cations and 2 chloride anions. Again, the anion is easy to forget to put that 2 in front of there. I wouldn't be surprised if you see me forget to do that at some point this evening. Okay, sodium nitrate. Don't forget your 2's. So I have my sodium cations. They are aqueous. And my nitrates, they are also aqueous. And I leave my lead 2 chloride alone because it is insoluble and it is a solid. Okay, double check, make sure everything's balanced. So leads are, nitrates, sodiums, and chlorides. So everything is balanced. This is my complete ionic equation. Let's cross out our spectator ions and make a net ionic equation. Okay, so my lead is definitely not the same, but I have 2 nitrates on both sides. Those are spectators. I can do the same thing with my sodiums and not my chlorines because those are not the same. And now I can write my net ionic equation. It is going to be much shorter. That is aqueous plus my 2 chloride anions. And that gives me lead to chloride as a solid. Again, if you were going through this and you didn't have this too, because again, it's really easy to forget, hopefully you would at least pick it up in the net ionic equation and go, wait, this is not balanced. And that should prompt you to go back and check your complete ionic equation and then your molecular equation as well. Okay, I'm going to need to add in an extra page here. So let's add in an extra page, and we'll just have to do a little working back and forth, which means that I need to see what my problem is. Okay, so sodium phosphate and potassium nitrate. Okay, so this is C. So we have sodium phosphate, 3PO4. I'll leave a little bit of space, plus I think that was potassium nitrate. Leave a little space. Let me just double check that. Sodium phosphate and potassium nitrate. Great. Okay, so first I'm just going to predict products, and then we'll go back and do solubility rules. All right, so this is going to give me sodium nitrate and potassium phosphate. Okay. All right. And now let's balance. Let's see. I need 3 of these guys. 3 here, and I already have 3 there. So I'm set. Now let's do our solubility rules. Okay. So our first one is sodium phosphate. Again, sodium here, they are all soluble. There are no exceptions. So sodium here, phosphate is going to be soluble, which means also sodium nitrate is going to be soluble. Okay, let's do potassium nitrate. Again, just like sodium, all your potassium cations are going to be soluble, just like all your nitrate ions are going to be soluble. So potassium nitrate is also soluble, as well as potassium phosphate. Okay, that's everything. So everything is soluble in this equation. This is your balanced molecular equation. Let's turn this into a complete ionic equation. Okay, so I'm going to have 3 sodium cations. They are aqueous, 1 phosphate, but it is also aqueous. Okay, now I'm going to have 3 potassium cations and 3 nitrate anions, also aqueous. Okay, keep going. 3 sodium cations and 3 nitrate anions. Great. And now I have 3 potassium cations. Oh, it's going to be a little bit of a squeeze. Okay, and my phosphate anion. And that is aqueous. All right, so let's double check and make sure everything is balanced. So 3 sodiums, 1 phosphate, 3 potassiums, 3 nitrate. Yes, okay, so everything is balanced. Great. This is our complete ionic equation. And now let's get rid of spectator ions. All right, so I have 3 sodium ions on both sides, so I'll get rid of that. I have 1 potassium, okay. Phosphate, 3 potassium, yes, and 3 nitrate. Okay, so you're probably wondering at this point, you've just crossed everything out. So what do you write for your net ionic equation? Well, usually you write either NR for no reaction. This means no reaction. Or you can even say no net ionic. Again, it depends on if you're doing this for a homework or a test, what your professor or what your teacher wants you to do. So basically what you've done is you've put 2 salts together. Everything is soluble, so you've got a bunch of cations and anions floating around, and they just stay floating around. So there is no net ionic equation for this one. Okay. Let's go on to the next one. So this is going to be lithium phosphate and aluminum sulfate. Let's make sure there are no other questions. Okay, I kind of get going with these. Lithium phosphate, aluminum sulfate. Okay, let's get D. lithium phosphate and aluminum, was that aluminum sulfate? Aluminum sulfate. Okay, so aluminum sulfate. So remember aluminum, that's one that's easy to forget, is a +3 cation. Okay, so now again, double replacement. We'll make lithium sulfate and aluminum phosphate. Okay, I'm just making sure that I've made neutral compounds. Now let's balance this. So I am going to need, I'm trying to balance my lithiums here. Actually, I'm going to need to put a 2 in front of here and a 3 here. So I have 6 lithiums on both sides. This gives me 2 phosphates, I've already got 2 aluminums, and that gives me 3 sulfates. Okay, so this is now a balanced equation. And I am just going to, that D there is kind of bothering me. It looks like part of the reaction. All right, now I need to decide what is soluble, what is insoluble. So what you can already probably see here is I've got some lithium salts, which are always soluble. There are no exceptions. So let's go ahead and make those lithium salts soluble. So our lithium phosphate is soluble and our lithium sulfate is also soluble. Now let's check out our sulfate rules. So if I go back to my sulfate, these are mostly soluble. I do not see aluminum in here, so that's totally fine. So that means this aluminum sulfate is soluble. And now I need aluminum phosphate. So if I go down, so here's our first time that we're really using phosphate. So phosphates are mostly insoluble, with these guys being the exceptions, meaning they are soluble. So this is an easy thing to get flip-flopped. So at least the way that this table is organized, you first have your mostly soluble salts, and then you have your mostly insoluble salts. And some books I have seen will actually break this up into 2 tables so that students don't get them mixed up. So anyway, so our phosphate salts are mostly insoluble unless it happens to be an alkali metal or ammonia. And you can see here that aluminum's definitely not an alkali or ammonia, so this is going to be our solid, this is going to be our precipitate. So we know automatically that now we definitely have a net ionic equation, and we're not going to have a no reaction. Now that we've got our molecular equation complete, let's go on to our complete ionic equation. So again, I'm going to take each soluble salt and break apart into cation and anion. Now I'm going to have some, I'm going to have to make sure I do my multiplying right because I have 6 lithium cations here. Otherwise my balancing is going to be off. But it is something that hopefully you catch as you do this and you check your balancing. Okay, so 2 aluminum, that is soluble. And we have 3 sulfate, that is soluble. Oops, let me put my charge in. All right, so going on to products. Again, I have 6 lithium cations. These are soluble. That is an I, okay. 3 sulfates, also soluble. And then my aluminum phosphate just stays because it is insoluble. And that is a solid. Okay, so again, just double check and make sure everything's balanced. So my lithiums are balanced. 2 phosphates, 2 phosphates, 2 aluminums, and 3 sulfates. That's great. That's fantastic. Now I'm ready to get rid of my spectator ions. So the lithiums go, and the sulfates go, and that's it. And so my net ionic equation is 2 phosphate anions plus 2 aluminum cations give me 2 aluminum phosphates. Now, the nice thing about this example is this is a balanced chemical equation. It is a balanced net ionic equation, but it can be simplified, right? So I can divide by 2 and make all my stoichiometric coefficients go to 1. So this is also a completely fine way to write this complete ionic equation. So both of these answers are valid for your complete ionic equation. It's just the bottom one has been simplified. Okay, let's make sure there are no questions. Great. Let's back up. Let's go to our next question. Okay, so this is our last one that we're going to practice molecular complete ionic and net ionic. So we have copper 2 chloride and sodium hydroxide. All right, so copper 2 chloride and sodium hydroxide. All right, let's get products first. So let's do our flip-flop. We'll go our copper 2 hydroxide, and we've got sodium chloride. Now let's balance. I need 2 hydroxides. Now I need 2 sodiums, which means 2 chlorines, and I've already got that. Okay, that's great. Now let's determine solubility. Okay, so chloride is one of those ones that, again, mostly soluble, and it's just got a few exceptions here, but copper is not one of those. So this copper chloride is soluble. Now, sodium hydroxide, so there are a couple ways to think about this. I noticed the sodium first, which means it's soluble because there are no exceptions. So sodium here is going to be soluble, which means it's also going to be soluble for sodium chloride. That's great. So the last one I have to do is just my copper hydroxide. So let me check out my rules for hydroxide. So hydroxides are mostly insoluble, which means as long as copper is not in the exception, it is insoluble. So yes, so my copper hydroxide is insoluble, so that is a solid. Okay, so that is our molecular equation. Let's go on to our complete ionic. And you can see kind of as we move through these, we start to move a little bit faster. You kind of start to get in the groove. Hopefully you start to get in the groove of these, and you see that they're really, it takes a lot of writing, but they're not so bad. Okay, don't forget I've got 2 chloride anions, and I have 2 sodium cations and 2 hydroxide anions. All right, and now for products. Okay, so my copper 2 hydroxide just stays because it is insoluble, and I'm going to have 2 sodium cations and 2 chloride anions. Okay, great. And let's make sure it's balanced. So copper is balanced, 2 chlorides, 2 sodiums, 2 hydroxides. All right, so we're balanced. Let's get rid of those spectator ions so we can write our net ionics. So no, I'm not getting rid of copper, but I am getting rid of chloride. I am getting rid of sodium, and my hydroxide just stays there. Okay, so let's write net ionic. So I'm going to have my copper cation plus 2 hydroxide anions give me copper hydroxide, which is a solid. So again, just double check, make sure it's balanced. We're good. And that is my net ionic equation. Okay, so that's it for the practice for just taking a reaction, predicting products, and then doing complete ionic and net ionic equation. Let's go on to the next type of problem. Okay, so this is a little bit different way of thinking about your solubility rules. So what we want to do is we're really putting ourselves in the teaching seat here. So we want to write a molecular reaction that will produce each of these insoluble salts. So you can think if you were the one who was giving an example or teaching this concept, how would you write an equation that would give you iron 3 hydroxide, as an insoluble salt? Well, of course, there are a couple ways to think about this, but I think about this as kind of moving backwards from your net ionic to your molecular. So I'll show you kind of how I think about this. So if I'm going to take equation A, and I think first of, let's see, that's iron 3 hydroxide. So that'll be that. That means that I need to have something with an iron 3 cation and something with a hydroxide anion. But I need both of these to be aqueous, if that makes sense. So that one's going to be solid, and you can put a 3 there, but really we're just kind of thinking about this. We're not actually writing the equation yet. So what I want to do for my reactants for this reaction is I want to go, okay, I need some kind of cation I'm going to be sure that some kind of anion that's going to be sure that iron is going to be soluble. So there are a lot of possibilities for this. I tend to go to the ones with either no exceptions or few exceptions. So like I think of nitrate as a great anion to make a soluble salt. So if I have iron 3 nitrate, I know it's going to be soluble. So iron 3 nitrate looks like this, and that is going to be a soluble salt. So now I need to react with something that's going to give me my hydroxide anion, but also it needs to be soluble because I need it to be aqueous. So hydroxides are mostly insoluble, but again, I tend to go for my cations and anions that either don't have exceptions or just have a few exceptions, and I love the alkali metals. So let's make this sodium hydroxide. And that, of course, is going to be soluble. Oops, I didn't write my AQ after this. So that is aqueous. And so now you can see if I am predicting my products just based on these two reactants, I'm going to flip-flop cation and anion, which means I'm going to predict my products to be first sodium nitrate. I'm going to have to crunch a little bit. And then iron hydroxide, which is exactly what I want. I want that iron hydroxide. And, of course, sodium nitrate is soluble, and we already know that our iron hydroxide is insoluble. So the last thing to do here is to balance. So I need a 3 here and a 3 here, and that is a balanced chemical equation. So this is a balanced molecular equation that will produce the insoluble salt iron 3 hydroxide. Okay, I hope that makes sense. Let's go ahead and go on to part B here. So strontium sulfate, and maybe what I should actually do is, so this was iron 3 hydroxide. Just go ahead and get the molecular formula up. So strontium sulfate, because that might make it easier to apply these rules. So strontium sulfate is insoluble, which means that I really wanted it, oops, that's an S. I need to form some salt that is going to give me a strontium cation that's soluble, and of course a sulfate anion that is soluble. All right, so strontium, let's start with strontium. Again, I go to my ones that are mostly soluble. We used nitrate last time because it's kind of my favorite, but let's maybe use one of the halogens. Let's make it strontium chloride because that is absolutely going to be soluble. So let's say strontium chloride, and that will be aqueous. And now I need a soluble salt for my sulfate. So let's make it maybe potassium sulfate. Again, there are obviously a lot of different choices that you can do here. You don't have to do the exact ones that I do. This is another type of problem that if you're working on it kind of with a friend, you might have two very different answers, but they're both the right answer. So you can see if I react these two together, then I am going to get my strontium sulfate, which is insoluble. And then I will also get potassium chloride, which is soluble. And if I balance this That is already balanced. So that is the molecular reaction that I need for this insoluble salt. Okay, let's keep going. So I like these kind of problems because they make you think about solubility rules in just a little bit different way. Okay, so magnesium hydroxide. Here is our molecular formula. This one is also a nice problem because, and the previous one as well, because it's making you use your naming rules too. That's something that's very easy to lose if you're not practicing as you're taking chemistry. And then, of course, you get to the exam and it's like, oh, how do I name these? Okay, so magnesium hydroxide. Let's see what two ions I need. So I'm going to need something with magnesium and also something with hydroxide. Okay, so let's get a magnesium. This is going to be pretty easy. Again, let's go back to nitrate because it's so easy. Okay, so magnesium nitrate. And that, of course, is going to be soluble. That's for the cation. And now something with hydroxide that's soluble. We can use sodium hydroxide again. Why not? Because we know it's soluble. I mean, you could always shake it up and go like potassium or lithium hydroxide. So this is soluble. And so if I'm going to predict products here, of course, I'm going to get my magnesium hydroxide, which is what I want. And I'm going to get sodium sulfate again, which is soluble. Now let's balance. I need 2 here, 2 here. That's it. And that is the molecular reaction we need. Okay, let's keep going. So part D, I need chromium 6 phosphate. Okay, this is interesting. So chromium 6 phosphate is going to be this. Let me just check my mental math. Yes, that's 6 and -6. Okay, just want to make sure you make a neutral compound. Okay, so chromium phosphate. I need something soluble with chromium and something soluble with phosphate. Okay. So for my chromium, again, I'm going to go for an anion that I know is going to be soluble. So let's maybe go for our bromide anion. Why not? So chromium 6. It's also nice. I like using cations and anions that either have a +1 charge for the cation or a -1 charge for the anion, because I just find it easier to make neutral compounds at that point too. Because you could use something like sulfate if you really wanted to, but then you've got to maybe deal with a little bit more difficult mental math, and I like to make that as easy as possible. Okay, so that was our chromium bromide, which is aqueous, and now I need a soluble phosphate salt, so let's go potassium this time. So potassium phosphate is nice and soluble. That is aqueous, and so this is going to give me potassium bromide, which of course is aqueous, and then it's going to give me my chromium phosphate, which is insoluble or solid. So let's balance this up. I need a 3 here. Oh, but actually I need a 6 there, don't I? Okay, so I have 6 bromides. So you can see when you're balancing, usually it doesn't matter where you start, but sometimes it does. But you can always go back and change things up, which means I need a 2 here, which gives me 2 phosphates and 2 phosphates. So now this is a balanced chemical reaction. Okay, let's do one more. Let's do part E. So I have nickel to carbonate, which is just going to be NiCO3. That's getting a little bit crunched. Okay, so nickel carbonate means that I need to have something soluble with my nickel 2 cation and my carbonate anion. So for my cation, let's go nickel. why don't we go back to nitrate? We'll just use a lot of N's. So nickel nitrate, nice and soluble. And then for my anion, for my carbonate, let's see, we'll go lithium, why not? So lithium carbonate, and that is soluble. All right, so I'm going to predict products down here. So this is going to give me my nickel carbonate, which is insoluble. And I'm also going to get lithium nitrate, which is soluble. So the last thing I have to do here is I have to balance. Let's put a 2 here. And actually that's it for that balancing. So that is my molecular equation for the insoluble salt. So in this problem, you had to think like you were going to teach the problem, which is always a nice thing to do. Okay, let's go on. All right, so now that hopefully we're comfortable with our solubility rules, we are going to move into doing a little bit of solution stoichiometry with our solubility rules as well. Okay, so this problem reads, what volume of a 0.1 molar sodium phosphate is required to precipitate all of the lead-2 ions from 150 milliliters of 0.25 molar lead-2 nitrate. Okay, so what we've got is we've got a solution with lead-2 in it, and we just want to make sure we precipitate all of that out. So we want to get all of the lead out of solution. This is, well, they don't actually do this, but this is something when you're dealing with wastewater that you might want to precipitate all of, say, a heavy metal out of the water so that you can clean it. Although they don't actually do this in wastewater treatment plants, but it's an idea that they use. Okay, so what I think the best thing for this one, we've got a lot of information because we've got some concentrations, we've got some volumes, we've got a couple of different compounds floating around. Let's go ahead and get a balanced chemical equation, and I'm going to do a balanced molecular equation for this. So we have sodium phosphate, and we're going to react it with lead-2 nitrate. So let's just get our reactants down. So sodium phosphate is going to be this, and I am reacting it with lead-2 nitrate. So that is going to be this guy right here. Okay, so first let's just predict products. You can see how we're already kind of doing the same thing that we did in the very first problem. Okay, so this is going to give me sodium nitrate. Great. And then it's going to give me lead-2 phosphate. So that is going to look like this. Oh, nope, not a 3. Sorry, that's a 2. I got to watch my mental math. Okay. So now let's balance this equation. I need a 3 here. That gives me 3 nitrates. And I need a 3. Oh, I'm going to see, I started in the wrong place. Okay, let's back up. I think it's going to be better to maybe start with my phosphate because I'm going to have multipliers. Okay, so I have 2 phosphates. See, that makes this 6 sodium, which makes this 6 nitrate, which puts a 3 in front of there, and now I'm balanced. Again, whenever you're balancing equations, you just pick a place to start, and you start, but never be afraid to stop and rewrite and do something differently, because sometimes it is better to just abandon your first attempt and do a clean, fresh second attempt. Okay, so now that we have a reaction, what we're trying to do is we are trying to precipitate all of the lead-2 ions. So I really want to make sure, first of all, that this is insoluble, and I want to make sure that all of these guys are soluble. So let's check solubility rules. Okay, again, we know that anything with sodium is going to be soluble, so I'm going to go ahead and put that in here. So I know that my sodium phosphate is going to be soluble, and my sodium nitrate is going to be soluble. nitrates, we know that these are all soluble. So I'm going to go ahead and put that there. So let's double check again my lead phosphate. So if I find phosphates, phosphates are mostly insoluble anyway. And of course, the only soluble ones are my alkali metals and ammonia. So this guy is definitely a solid. It is going to precipitate out. So the problem did set us up for success. It went ahead and told us our two reactants that is going to produce our precipitate that is going to pull all of those lead 2 ions out. Now we need to start dealing with our solutions with our solution stoichiometry. Okay. So the first thing that I want to know is I want to know how many moles of lead 2 nitrate I actually have, because I've got a volume and I've got a concentration, so I can get my moles of that. Okay, so I have a concentration of 0.250. Now remember, molarity, I'll just maybe put this up here in a different color. Molarity equal moles of solute over liters of solution, just as a reminder, because I'm going to use this. So instead of writing capital M here for molarity, I'm going to go ahead and break it apart. So this is moles of my lead 2 nitrate. And that is over 1 liter of solution. Okay, so just so you know where I got those units from, those are the units of molarity. Okay, so if I take this and I multiply it by my volume, I'm going to have to convert to liters. That will give me my moles of lead nitrate. So I have 150 milliliters, which is 0.1500 liters. So you can see that, and this is liters of solution. So you can see that my liters cancel, and this will just give me my moles of lead nitrate. So when I do that calculation, I have done that calculation, I get 0.375 moles of lead nitrate. Okay. So now that I know how many moles of lead nitrate that I have, I'm going to use my balanced chemical equation to figure out how many moles I need to react with my sodium phosphate. So I'm going to take my moles of lead nitrate that I just calculated, moles of lead nitrate, and I'm going to use my stoichiometric ratio to convert to moles of sodium phosphate. Okay, so to cancel out my moles of lead nitrate, that has a 3. Again, this is just coming from my balanced chemical equation. It's either you can think of this as a 3:2 or a 2:3 ratio. So that is 2 moles of sodium phosphate. I realized I forgot to write my moles in there. That's moles. Okay, so this calculation will tell me, because my moles of lead nitrate cancel, how many moles of sodium phosphate I need. So when I do that calculation, I get 0.025 moles of sodium phosphate. Okay. So if I go back to the problem, because now I know how much sodium phosphate I need, but have I answered the question of the problem? And the problem asked me what volume I need of sodium phosphate, not how many moles. But I'm very, very close, because at least I have an amount of moles of sodium phosphate. So now I just need to figure out what volume, and I have a concentration. So let's maybe do this one with our formula for molarity. So I know my concentration is my 0.1 molar. Again, this is my sodium phosphate. So with all of these problems, make sure you're really specific with your units. You don't want to just be writing down moles, because you can see I've got moles of different compounds. So I know it takes extra time, and when you're trying to work through a lot of problems, you really just want to skip this step, but don't skip this step, because just almost always students end up using the wrong number of moles. They've actually tried to do the problem right, but they haven't written down their units, and it has unfortunately given them the wrong answer. So make sure you get your units in. Okay, so again, I'm using my formula for concentration. I know my moles of sodium phosphate, so I'm going to put that in the numerator. Sodium phosphate. And what I'm solving for, I'll call this X liters of solution of sodium phosphate. So again, I'm solving for my volume here. So when I do this calculation, and I did do this calculation, I get X is equal to 0.25 liters of sodium phosphate. And that is the volume of sodium phosphate that I need. You could also write this as 250 milliliters if you wanted to, just because they gave us milliliters, but they didn't specify that they wanted milliliters, but just so we have it. So I'm going to need to add at least 250 milliliters of my sodium phosphate solution to my lead nitrate to make sure that I precipitate all of my lead nitrate out. Okay, so I think we'll actually end there. I did have one more problem, but it's a bit of a long one. So maybe we'll put that into another live stream at some point. It's a limiting reactant problem, which is good to practice, but because we're getting on to 8 o'clock, we will not practice it tonight. So thanks so much for joining us. For next week, there will be no live stream. I am actually gone next week. But as always, please let me know what kind of problems you would like to see worked in any live stream. You can either leave me a comment on YouTube, you can leave it on this live stream later, or you can send me an email, or you can send a message to me on Facebook. So thanks so much for watching tonight, and I hope the rest of your Wednesday is great. Bye.